Hi everyone, let us solve a couple of online homework problems that deal with Raoult's Law, Osmotic Pressure, and Henry's Law. Now, many of the problems that you'll see on an exam, you may not be able to take the data that you see and put it directly into an equation. You may need to manipulate some numbers, or you may need to extract more information from the data that they give you before you actually use an equation to solve for what's asked for. Here, what do we have? We have pure chloroform and the vapor pressure. And they are preparing a solution with acetyl bromide in chloroform, and then they're asking what is the partial pressure of chloroform vapor above the solution. So this is a vapor pressure problem, and we do know the vapor pressure. Do I know that? Vapor pressure equation. The partial pressure of a solvent equals the mole fraction of that solvent times the vapor pressure when the solvent is pure. That is Raoult's law. They are asking for the partial pressure of chloroform, but we don't know the mole fraction. And whenever you have a mole fraction, that is part over whole times 100%. Oh, no, not times 100%. This will be a decimal. This will be less than 1. Part over whole. We know that because you've learned that vapor pressure is a collective property and it's vapor pressure lowering. So we're going to multiply this pressure of the pure solvent by something less than 1, and we'll get a smaller partial pressure. Okay, well, mole fraction. We have chloroform, CHCl3, and we need the moles of that, 92.8 grams times 1 mole, and the molar mass of chloroform is 119.4 grams per mole equals 92.8 divided by 119.4, 0.777, and you don't want to round to too few significant figures until you get to the very end, and then you round to the appropriate number of sig figs. They want 3. For the acetyl bromide, CH3COBr, that actually is a liquid as well. We're mixing a liquid in liquid mixture. 88.7 grams times 1 mole over the molar mass for acetyl bromide is 122.95. I was going to round, but I'll leave it at 122.95 grams equals the number of moles of acetyl bromide is 0.7214 moles. Because we want the whole, we should total these up. Plus 0.7772. Okay. 1.5. It rounds to 00. Actually, it rounds to 1.50. That's the total moles. Because we want the mole fraction of chloroform. I think we're ready to plug in numbers. The partial pressure of the chloroform vapor is equal to the mole fraction, 0.7772, over 0.7. Oops. You got to take the whole, not just the acetyl bromide part. 1.50 times, we have 262 millimeters of mercury. That is the vapor pressure of the pure chloroform. That equals, let's see, 0.7772 divided by 1.5 times 262, and the units of the partial pressure will be in the same units as the partial pressure of the pure solvent. We're going to round to three significant figures, 136 milligrams of mercury. Now, think about that number and think about what this means. The vapor, right? The vapor pressure of just the chloroform is 136 millimeters of mercury. Vapor pressure of CHCl3. But that's not the total vapor pressure, right? Because we do have a liquid here, acetyl bromide. We just don't know, they never told us the vapor pressure of pure acetyl bromide. But if they did, we would be able to figure out the total pressure. And because we have both partial pressures of those two liquids that turn into gas, then we could also figure out the mole fraction of each component in the vapor, okay? Which will likely be different than the component or the mole fraction in the liquid. I don't have that problem set up for now. Maybe we'll take a look at that later. But that's the answer. That's all they want. The partial pressure of the chloroform, or it's really the vapor pressure of just a chloroform component of this solution. Next, we have an osmotic pressure problem. And they want to find the molar mass. They want us to find the molar mass. I'll read the question in just a bit, but the osmotic pressure equation is capital pi or uppercase pi equals mRT, that is molarity. The symbol for molarity, or the unit for molarity, is big M, but we know also that can be broken down to moles per liter. This is 0.0821, and let me just put the units because I want to make sure that we end up with a unit that makes sense for osmotic pressure. This is K, so the mole, well no, the molarity is moles per liter, so the liters and the moles will cancel out. The K's, Kelvin, will cancel out, so we're left with atmosphere. This will be ATM. Okay. So I gave a hint. This is the same as moles of solute over liters of solution. That's going to be important because remember when I said that sometimes you can't just start plugging in numbers to get out what you're asked for? They're asking for a molar mass. Molar mass is not anywhere in this equation, but we know that molar mass is grams per mole. And we do have moles here. Let's see what the other data tell us. We have 126 milligrams of an unknown protein. Why don't we change that right now to grams? 126 grams of the unknown. Happens to be a protein. And then we have that in 5 milliliters of solution. Let's change that into liters. Why? Because there I have grams, and there I have liters. So just break up the molarity into its mole over liter component. Ooh, they gave us the osmotic pressure and the temperature. So the osmotic pressure they gave us, ATM, and the temperature is 298 K. what do we have? We have the osmotic pressure, 0.0294 equals. We don't have the molar mass. Oh, we don't have the molarity. And not only do we not have the molarity, we're being asked for the molar mass. Now's a good time. Just break it up and see if we can start filling in blanks. Because if we break it up, we have moles on top, which I don't think we have anywhere here, and liters of solution on the bottom, which we actually do have. So do you see how we're able to reduce this to one unknown variable? 0.0821, 298. What I would do is, what I would do is I would cross multiply first. 0.0294 times 0.005. We have a number on the left. We got to bring these two numbers over to the left also, so we're going to divide by 0.0821 equals, divided by 298 equals. Small number. Do we expect a small number? It's a protein, right? You don't need a lot of it for it to have a significant mass. The moles of protein is 6.008 times 10 to the minus 6 moles. And we have grams up there. We're going to bring those two numbers together. And the molar mass is grams per mole. All you have to do is divide one by the other. And we should get a molar mass. And hopefully it makes sense. I have that number saved already, the denominator. 0.126 divided by, oh no, 0.126 divided by the answer. Yes. And let me get out of scientific notation. They want this into 3 significant figures. So that's 2, 1, 0. Well, that's how do I represent 3 significant figures if the number is 20,970? Let me go back to scientific notation, and we'll give 3 significant figures. 2.10 times 10 to the 4, and that is grams per mole. So it's large. That's the same as 21000, right? 21,000? Okay, 21,000 grams per mole. But it's a protein, and proteins can get that large. They could be actually much larger. Okay. For the first, go ahead and circle your answer. For the first 2 problems, I should have asked you to try it on your own just to see if your notes are useful. So here's Henry's Law problem. Why don't you give it a shot and use your notes, and if you cannot do this problem with your notes, then there might be a disconnect between lecture, the notes, and applying those notes or concepts that you've learned in lecture. Okay, go ahead and give this a shot. Okay, if you're not done, go ahead and pause. Let me show you how I would do this. It's Henry's Law. Heck, let's pretend we don't even know that. Well, actually, it says it here also. So, argon, what is that? That is the constant. So Henry's Law is concentration equals lowercase k, subscript capital H, uppercase P. This is called the Henry's Law constant. We'll figure out its units in just a bit. But P is the partial pressure of the gas. what is this demonstrating? It's demonstrating that with pressure, you could make gas more soluble in liquid if you pressurize it. So this is the partial pressure of the gas. And this is just plain old concentration, and it's a molarity concentration. Remember that trick last time? Okay, we could use big M, but why don't we break it up into moles per liter just in case, right? Just in case we have to solve for one of these two, either the volume or the moles. Okay. Data's all up here. Why don't we try to plug in without writing out all the data? Concentration. We asked for mass. Oh my. I don't see mass anywhere in the equation, but if you take mass times the molar mass, you get moles. Okay? And we do know that we're working with argon. Argon has a molar mass of 39.95. This is what I meant by trying to extract data that you don't see, or trying to manipulate the numbers that you do see to give you more information that then you could start using your equations. Okay. Since we get given the identity, we could definitely pick up from the periodic table the molar mass. All right. What can we do? Oh, there's a volume. We have moles over 0.325 liters equals kh. Oh, I promised that we would figure out the units here. Well, if this is an atmosphere, and this is its molarity, big M, or moles per liter, that has to be moles per liter over ATM to cancel out the ATM of the pressure. Typically, Henry's law constants are in molarity over ATM. And we have that right there, molars over ATM. Okay, that's our KH. And then our partial pressure of the gas, I hope they gave it to us. There, 1.84. Okay. We're not solving for the mass directly, but if we know the moles, we know the molar mass, we get the molar mass. Moles equals, just cross multiply, 0.325 equals times 1.4 times 10 to the minus 3 equals times 1.84 equals 8.372 times 10 to the minus 4 moles. We're going to use the molar mass. We need to do grams over mole, so we have to multiply by 39.95 grams over mole. That will cancel out moles. And we'll be left with grams. So I have that number saved, times 39.95. Let's go to scientific notation. That's how many grams, huh? We have equals grams equals 0.12 digits, 0.033 grams. Circle your answer. That's not a lot. It is a gas, and they're dissolving it in just 325 milliliters of water. That'll be your grams of argon. Okay. Maybe we'll try more in-depth problems, more complicated problems, but that was a good start when we talk about colligative properties and solubilities of solids and gases and liquids.